Hello, this is Concrete Path. Here we have the lecture for effective stress, effective stress, effective stress. So this concept is given by that Terzaghi, concept given by Terzaghi for your fully saturated soils, for fully saturated soils. Okay, I would say we we have the interaction of that soil solids and water interaction is there. They are going to interact. There is interaction of those soil solids and water, and it can be, this interaction can be either chemical interaction or it can be physical interaction, chemical or physical interaction. Now for the physical interaction we say that, for the chemical interaction we already know that it would talk about the structures forming because of that reaction between the water and the soil solids. So it talks about the bonding forces between those soil solids and the water. And the physical one is talking about the rolling, sliding, those physical actions, rolling, sliding of those solids, in the soil mass, So we have talked about the chemical structure. Now for the physical interaction, of those soil solids with the water, we have this concept of that effective stress. We study this physical interaction by the concept of effective stress. So before getting into the effective stress, we have to get into the soil. What are the kinds of stresses that are going into playing an action in the soil? So we have three kinds of stresses that we are going to talk about. So let's try that. We have three kinds of stresses. In that soil mass, in the soil mass. Okay. Number one, is there that we call it as total stress. Total stress. So we denote it as a sigma. Total stress is there. Okay. So we are going to take a soil mass. Let's say this is your soil mass. This is your soil mass of height h. And there's some weight also above. There's some surcharge. We can call this one as surcharge. There's some loading above. This surcharge, we say that this is your surcharge because of that external loading. Let's say that there is some building, so it's having some surcharge of Q equals to, let's say, 100 kilonewton per meter square. Let's assume that this is your surcharge, and there's some height of the soil mass also. This is your height of the soil mass, and let's say that let's zoom in. I would say we are having few soil particles. Let's say these are your soil particles. Okay. So we're going to take a section. Let's say we are going to take a section somewhere here. So this is our section we are going to take. Let's take that. This is your section. We can take it a curved way, in a wavy fashion. Let's say this is your section, XX section. So on that section, I would say, how do you calculate that effective? How do you calculate that total stress? So total stress says that I am the stress that is actually weight above that cross section, and divided by the area of that cross section. If I have that in that 3D, I would say that you have this section, some sort of section is there. Let's say this is your section, and we want to talk about that particular section in 3D. So there would be some three-dimensional that, such that there is some cross-sectional area. This is your cross section, and on that cross section, I would say, what is this total stress? So this is the weight above that cross section divided by the area of that cross section. So let's say that there is some weight above W divided by area cross section. That is your total stress. Weight above, we can write. So that's your total stress. Let's take that simple case that we are having a soil mass. Okay, and there is some water table. This triangular inverted triangle. This says that this is the water table. Okay, groundwater table. This is your groundwater table, and somewhere here there's some cross section XX, and on that cross section there is a point. Let's say there is a point O. I want to say what is the total stress. What is the total stress at that point O? So total stress at that point O. I want to calculate total stress at point O. At point O on cross section XX. Okay, and there's some surcharge also. Let's say that there's some surcharge of Q kilonewton per meter square on the top of that soil, and the height of that top one is there H1. This is the height of the initial first soil mass. Let's say this soil mass is dry because water table is not there, so we can say this is your dry soil. Let's say that this soil is dry, and after that we can say that below that soil, that is saturated soil because we have water table there. So this soil, we can say this is saturated soil, and let's take that height as H2, this part as H2, total H2. So we would say what is this total stress at that section. So stresses at that point O would be calculated as that total forces. It's actually total force. It's actually total weight above divided by area of the cross section. So let's say that the area of the cross section there is A, and we want to say what is the weight above that cross section. So for the weight above that cross section, let's say that your kilonewton per meter square is acting for an area of cross section A, such that total force of Q into A is there because of that surcharge, plus there's some dry density, dry unit weight is there because of this dry soil, and we are having that area of the cross section, and we are having this height of H1. So this is the total force. Do you know that gamma into volume is your weight? So I would say we are having one more that you what you call as force. That's because of that double gamma d area A cross section into height H1. Plus similarly we are having that gamma sat. So gamma sat is there. That's gamma, because of the gamma sat we are having one more force, area into H2. We can write gamma sat area into H2. So we can simplify further it. We can simplify it further that total stress is equal to Q plus gamma d H1 plus gamma sat H2. So that is the total stress at that point O. Stress at point O. Total stress at that point O. So we say that your total stress is a measurable quantity. This is your measurable quantity. We say it's a physical parameter, measurable quantity. Your total stress is a physical parameter that we can measure it by some instruments. Measurable, that means we can measure it. Let's say that, for example, we measure it by pressure cell. We call it as pressure cell, by which we can measure the total stress. Pressure cell. Okay. So it's simply that it's easy to calculate because it's only saying that what is the total weight above that particular cross section divided by area of the cross section. Cross section we know, and we know what is the total weight above that soil, above that cross section. That is easily measurable. So we measure it by your pressure cell. So this is your physical parameter and measurable. Okay. Let's go to second kind of stress. Second kind of stress. Second kind of stress, that's pore water pressure. Second kind of stress, that's pore water pressure. Pore water pressure. Pore water pressure. And this one we denote it by small u. Small u is your pore water pressure. So what does this means? This means some pressure in the pore water, in the pores. So I would say that this is the pressure because of the water, because of water present in the voids of the soil, in soil voids, in the voids of the soil. Isn't it easy? So what is the pressure because of water in the voids of the soil? So that's your pore water pressure. So this is also measurable. How do you measure it? It's measurable. So we can also measure it. So how do we measure it? We say that you want to find pore water pressure at any point, O. You do one thing. You insert standpipe, or we also call sometimes we can have a piezometer also. Piezometer. So we can have this instrument, that's piezometer, or we can take this standpipe. You insert this standpipe or piezometer at that point O, at that point O, at the level of point O, at the level of point O, and at that, then we say that how much water there is rise, that how much rise of water is in that pipe, in the piezometer. That's your That's your actually head because of, this is the head because of, this is the pressure head because of pore water pressure. Let's say that some h is the rise. Let's say there is some height of h, that is the rise of water in the piezometer, and that head is because of the pore water pressure. So let's try to understand that. Let's try to understand that. We say you have the soil mass, you have the soil mass, and you have the soil mass. Okay, let's say that your soil is dry. This part is dry, and water table is here. This is your water table, groundwater table. This we call it as groundwater table. Groundwater table. Okay. Now I want to say what is the pore water pressure at this point O on this cross section x. I would say you have to insert a standpipe or piezometer at the level of that point O. Let's try to insert that piezometer or a pipe. Let's say that you have this piezometer inserted here. Piezometer is inserted. I want to say what is the rise of the water in this what you call as piezometer. So the rise of the water is actually up to the level of groundwater, up to the level of groundwater. So this is the rise of the water in the piezometer. Let's say that this is some height of h, such that if this was h, let's say this was some h, let's say this was some h, and there is again same amount of h that has risen, risen in this what you call as uh, piezometer. If this was height h1, so we only have that rise of the water in this piezometer equals to h. That's actually the vertical elevation difference between the point O from the ground water table. So so this condition we can call it as this pore water pressure because of this head rise. That's the pore water pressure would be actually this is some water. So because the water is there, groundwater table is there, so we are going to take that that there is this is the rise of water. uh, this is the rise of water. So because this is the rise of water, I would say your pore water pressure is accounting the weight of the water. That's actually unit weight of water into height of h. So that is the pore water pressure. That's kilonewton per meter cube into height of meter. So that's your kilonewton per meter square. Okay. Here, if the liquid is some different, some other different liquid is there. Let's say mercury is there. If the mercury is there in this soil mass, the height would be corresponding to. So the pore water pressure would be corresponding to G times G mercury into gamma W into H. So that is your pore water pressure if we try to understand that in this way. Okay. So your pore water pressure actually is talking about that if this is the simple case. This is the simple case when there's no loading, external loading, when there's no loading, external loading. So at that time your pore water pressure is actually talking about that I would rise to the level of groundwater table. So I'm going to rise. So I'm going to rise up to groundwater table only. So that's very easy case when there is no external loading. Your pore water pressure rises in the piezometer only up to that level of water table. Whereas the water table up to that point, your pore water pressure would rise. Your pore water pressure would rise. Okay, so that's very easy. Okay, okay. Let's say that we this pore water pressure we also call it as neutral stress. Neutral stress. Neutral stress. As you have this particle, soil particle, this water, this pressure because of the water in the voids, it acts in all directions on the soil mass, soil solid. So this we call it as neutral stress because it acts in all directions, acts in all directions on that soil solid, on solid. So that's your neutral stress. Okay, that's your neutral stress. Okay. Now we will talk about that. What is the effect of that different loading conditions on what you call as on the pore water pressure calculations, on the pore water calculations. Let's go for that. Let's go for that. Let's go for that. I would write that. effect of external loading, effect of external loading, that we also can say this is surcharge, surcharge, surcharge Q, stress, this is stress, okay, surcharge Q, on calculations of pore water pressure, on pore water pressure U. What is the effect of that external loading because of the surcharge? This one is very, very important. This is very important. So let's go for that. Let's take the case number one. Let's that case number one is there. That case number one. If there was no, what you call as external load, no external load, that is the simple case. No external load is there. That we have already talked about. No external load is there. Okay. Let's have an example. Let's take example of that. I would say this is your dry soil. This part of the soil is dry. After that, we are having water table up to this point. Let's say this is water table. This is groundwater table. Or we can say this is water table. And I want to say what is this? What is the pore water pressure at the location of at this location? Let's say height is H1. This is the height of H2. And at this point, I want to calculate at this point O what is the pore water pressure. So I have to insert a what you call as piezometer here. Let's say that I have inserted the piezometer. I want to calculate what's the pore water pressure in this at this point. What is the pore water pressure at this point? So if this is the simple case, there is no external loading. We say that this is this corresponding to the case. Then that means your water table, up to the level of water table, your rise of water would be in the piezometer. So the rise of water would be in the piezometer up to the level of groundwater table. So up to this level, that's up to the level of groundwater table. So this height is actually H2. So this is the height of rise of that water in the piezometer equals to height H2. So this what you call as this we call it as initial pore water pressure. So we can write it as U naught. That's initial pore water pressure. Initial pore water pressure. Pore water pressure. And that would be actually equals to if there is water in this part and the soil is saturated here, so water is there, so I can write this is contributing to gamma W, and the height here is H2. So that's actually your pore water pressure. So actually we can say that what is the height, that's what would be the rise of height, so that's actually U naught by gamma W. So that is the height of that rise of that liquid in that piezometer. So I would say your U naught is actually initial pore water pressure, and this one we call it as static pore water pressure. Static pore water pressure. This is the static pore water pressure for your soil mass at that particular section, section O. Uh, Section O. So this is your U naught. That's initial pore water pressure at that point O. Okay. Now we can say, let's go for the case number two. Let's go for the case number two. That we are applying that what you call as that load. So case number two says that we are applying load. Load is applied. So we can say, but we want to talk about immediately after the load is applied. Immediately after the load is applied. We want to talk about the at that time when load was applied, and we want to talk about at that immediate time, immediately after the load is applied. So let's say that we have the same stuff here. We have the same stuff here. We have the same stuff here. Okay. Now we are going to apply that what you call a surcharge. Load is applied. Let's say that we are applying surcharge of that what stress, total stress equals to Q, such that this is some force applied divided by the area of the cross section, and let's say that because of this there is some increase, there would be some increase of water level. Let's say that first how that water level would be going to increase. Let's see how. So immediately after the load is applied, that surcharge is applied, I would say at that same time your soil grains would try to resist that. Soil grains would try to resist. Soil grains try to resist. Okay. Okay. And soil water is also trying to resist. Water is trying to resist. So water is also trying to resist. Okay. Now I would set a condition here. Now set a condition. Let's set a condition that I want that degree of saturation equals to 1. soil is saturated, and the soil is laterally confined. Soil is laterally confined. Laterally confined. You can think of a that you're doing this test in what we call as lab. So there we have some sort of cell in which your soil is placed, and this soil is not going to go any that there won't be any lateral strain for your soil. So that means your lateral strain for your soil is actually zero. Lateral strain for your soil is equals to zero. So that means laterally the soil won't be going anywhere. The soil won't be going anywhere. So and if the soil, and I would say if the solids and water is incompressible, if the solids and water is incompressible, so there's only one possibility that I would say there's only one possibility that only the one possibility is here that your what you call as uh, your water is going to run away. Water is going to run away. Water runs away. So your water is going to run away towards drainage phase. Drainage phase. Towards drainage phase. Okay. So because soil is not going anywhere, and it can't compress also, because it is incompressible. Solids are incompressible, but water is also incompressible, and you are not allowing it to laterally go anywhere. So there's only one possibility. If you have a drainage phase. Let's say we are having a drainage phase somewhere here. Let's say this is your drainage somewhere here in this arrangement of that what you call a cell in the lab. Let's say that. So you are having some drainage system. So water is going to run away towards the drainage phase. So I would say for immediately after the load is applied, that is resisted actually. So that is actually resisted by the water at that time t equals to zero. I can write at time t equals to zero, your water is now resisting for when I set this condition that if the lateral strain is zero. So this is very important here. So I have set this condition. I have set this condition that I don't want that lateral strain for your soil. I want it to be zero. At that time, that's only one possibility of that soil mass is there, that there would be loss of water. So that means water is now trying to resist. Water is trying to resist the change. That's the because we are applying the total stress of surcharge. That's extra surcharge of Q. So that because of that, there would be that resistance towards that change. So water is now going to resist that change, and that means your pressure. That means your pressure in the pore waters would be increased. So pore water pressure would increase now because water is trying to resist. So it would develop some stress. So now it would develop some more stress developed in the water. So because of that, we would say that pore water pressure has increased, and increase of pore water pressure, this increase of pore water pressure, we call it as excess pore water pressure. So we can call it as excess pore water pressure. So this increase of pore water pressure, we can write this increase of pore water pressure is equals to excess pore water pressure above the static above the static above the static pore water pressure above the static pore water pressure. So if I say that, what is the final pore water pressure immediately? What is the final pore water pressure immediately after the load was applied? So that's actually initial pore water pressure, that was static pore water pressure, plus that excess pore water pressure, excess pore water pressure. So that's your that final stress immediately after the load is applied. That means no stress is taken by solids. So that means no stress. That means no stress taken by solids at that time. No stress taken by solids at time t equals to zero. Taken by solids at time t equals to zero. But this is true for this condition when we say that lateral strain should be zero. When we say that lateral strain is zero. So this is actually a lab condition. So lateral strain, I want it to be zero. I am not allowing that because I have confined the soil specimen in a cell, so it won't go anywhere. It won't go anywhere. So only the possibility, because I am applying extra stress, so there would be loss of water. This is the only one possibility we can have for your soil mass. Now, if I say that there is lateral strain, I am allowing lateral strain. That means soil can deform in lateral directions. Soil can deform in the lateral directions. Let's talk about the second one. That's your lateral strain is allowed. Second one. Now there is a second possibility that if I allow lateral strain is allowed. lateral strain is allowed, that means your E lateral is not 0. So if there is lateral strain of the soil mass, that means some part of the stress would be taken by some part of the, yeah, we forgot one statement here that was very, very important. So we've got this excess pore water pressure, but how much is that excess pore water pressure? How much is that excess pore water pressure? This is because of because of the water that's trying to resist the change. How much it's trying to resist? So it's trying to resist the total stress of change because of that, because of the surcharge. It's trying to resist because of the surcharge. That's the extra stress we are applying in the soil mass, on the soil mass. So I would say your excess pore water pressure that has increased, that's actually equals to surcharge. That's external stress. External stress. So that's I would write, so this is your external stress applied. External load divided by area cross section. So that's your surcharge. So I would say your if no stress is taken by solids at time t equals to 0, so your excess what you call as surcharge is equals to, excess surcharge is equals to that's actually equals to um, Q. That's equals to Q. Um, Now because there is excess pore water pressure, initially what was the level of the water in the piezometer? Now we want to talk about that level of water table, level of water in the piezometer. Let's say that there was no, now initially it was static condition. Now I am applying that load. So we are talking now about immediate time, immediately, that at t equals to 0, when we applied that stress, external stress of surcharge Q. So at that time your excess pore water pressure increase. There is increase of pore water pressure, and that's equals to Q. And because of this pore water pressure, I would say, what is the final pore water pressure at this location? At this point O. What is the final pore water pressure at this point O? So this is very important here. Final pore water pressure at point O. What is that? That would be actually what was initially plus what is excess. So initially we had this value of gamma w into h2, gamma w into h2. Now there would be some increase, little bit of increase. Let's say there is some excess because of that. Let's say there is some increase. Let's say this is some increase of h3. This is some increase of h3 because of q. So we can write that. So we have now I would write, because we have increase of water level h3 uh, for fluid of water, for fluid of gamma w equals to that gamma equals to gamma w. So that means your q can be equated with that equals to in this way. That's your q equals to gamma w into h3. So I would say, what is the increase of that height? That would be calculated from this result, that what is the total stress we are applying? What is the total surcharge applied? Total surcharge applied and divided by the unit weight of water. So that's your increase of height. Increase of height because of that surcharge applied. So that would be some H3. So finally, I would say your excess pore water, that final pore water pressure at point O is actually gamma WH2 plus Q, we can write. So that's your final at that point O. So this was very, very important. So this H3 can be anywhere. It can be above that level. It can be somewhere here. It depends on the value of surcharge. It depends on the value of surcharge. Okay. So that's your very, very important conclusion, that if we talk about that immediate condition, that load is applied, and at that same time we want to talk about what is the increase of pore water pressure. At that time we say that for lateral strain to be zero, for lateral strain to be zero, your stress in the solid is not going to increase, but that means all that stuff, all that increase of stress is taken by that pore water. So there would be that stress developed in the pore water, that is extra pore water pressure. So that's your excess pore water pressure. Okay. Now finally I want to allow that lateral strain. Let's talk about that. I am allowing the lateral strain. Lateral strain of the soil mass is allowed. That means some stress. So some stress is taken by some of the surcharge. Some of the surcharge is taken by soil solids now. Some of the surcharge taken by solids also. Taken by solids also. Because there is deformation. That means there is deformation of solids in the lateral direction. There is deformation of solids. So because of the deformation, there will be stresses in the solids. So let's say that there is some stress taken by the solids. So that means, what is the excess pore water pressure now? Can you tell me what is the excess pore water pressure then? If some of the part is taken by what you call as some of the part of the surcharge Q is taken by solid. That means pore water pressure excess, it would be less than Q. Can we say that excess pore water pressure in the so that pores in the water would be less than the surcharge, total surcharge. So that's very one more conclusion we can draw here. So I would say for for your perspective, we can keep this one as important, that we are keeping lateral strain to be 0, and that means your excess pore water pressure is all taken by that's excess pore water pressure is equals to surcharge, total surcharge of Q. Okay. Now let's go to the second third condition. Let's go to the third condition. That's case 3. Case 3. Now there is case 3. Now load was applied. Okay. Surcharge is applied. Okay. Now we want to talk about value of pore water pressure at after a very long time. After a long time. That means after some years you are going to come again to the soil, to visit the soil. You are saying what is the pore water pressure you have in your soil mass? What is the pore water pressure you are having in your soil mass? So pore water pressure after a long time. After a long time. So what's going to happen now? We said that you had this system, you had this assembly, you had this height of H1 dry soil. There was water table. There is some saturated soil also. You are at this point O. You are inserted that is piezometer here. Okay, this was the initial condition. You applied the surcharge of Q. Now we are talking about the after a very long time. What is the thing we said in the first case? In the second case, case 2, we said that there would be some loss of water. So water runs away. Water runs away. Water runs away towards the drainage phase. Now to resist that increase of Q, water has resisted. Water has developed stress of U external equals to excess equals to Q. This was immediate condition. Okay. Now it wants to relieve that stress. It wants to relieve that stress now. Water wants to relieve that. Water relieves that stress now. Water wants to relieve that stress. Okay. Excess pore water pressure. So for that it has to lose the water. So it would lose the water. So it would lose the water till loss of water would be there. Loss of water would be there till your excess pore water pressure becomes 0. Till your excess pore water pressure becomes 0. So your I would say for the load applied there, but we are talking about the pore water pressure after a very long time. For that condition, I want excess pore water pressure should be 0. Excess pore water should be 0, because water is trying to resist. Because by water is trying to resist, it would lose a few part of that total water is going to be lost, and by losing the water, it would relieve that excess stress. So that means if the stress is lost, but if the stress in the pore water is lost, that means pore water pressure excess has been lost. So but by the force equilibrium, I would say now the water is not going to take that excess pore water pressure. So that means that should be taken by the solids now. That should be taken by the solids. If I say that summation of Fy equals to 0, so that means your Q should be taken Q into A. This is some force. It has to be taken by what you call as solids now. Taken by the solids now. Taken by solids now. Okay. Okay. That means it has to be taken by solids now. Okay. So that means there's I would say let's try that for the after a long time. After a long time, what's going to happen now? After a long time, excess pore water pressure becomes 0. So this loss of that excess pore water pressure, we call it as dissipation. So that is your dissipation of pore water pressure. Dissipation of pore water pressure. But this is not initial pore water pressure. This is actually excess pore water pressure. So that is actually, we call it as the dissipation of. What does dissipation means? This means loss of that. That is the relieving of this that those pores by relieving of that pore water by that amount of stress called as excess pore water pressure. So dissipation of excess pore water pressure. That's your okay. Dissipation of excess pore water pressure. Okay. So when there is excess that when excess pore water pressure becomes zero, so I would say what is the final pressure that's going to be present in the pore water. So this is the final pressure in pore water, in pore water, in pore water. So that's your final, that would be actually U naught, that was static pore water pressure, plus U external, U excess, sorry, but your U excess is equals to zero now. Your U excess is equals to zero now. So that means your final stress is actually static pore water pressure, and that we say that's your hydrostatic pore water hydrostatic pressure. That's actually hydrostatic pressure. That means it is similar to that of that if you have this water, that's your, let's say that this is your water in some sea. Let's say this is your that sea or a river. Let's say this is your sea, and I want to say what is the stress at this location, at a location of height, at height h from the tops, from the free surface. What is the total stress? What is the pressure at that point? I would say pressure at this location is equals to gamma w into height of h. That is the pressure. So that's actually hydrostatic pressure. And similar to that, now for this case, I would say what is the pressure? What is the pressure after a long time? So I would say you insert the pipe here, piezometer, and at that point, I would say your stress would be corresponding to the level of water table. That's actually groundwater table. So this is actually H, and your pressure is actually equals to gamma W into H, and that pressure is actually hydrostatic, and that's also equals to pore water pressure. That's similar to that of initial case number one. Okay, so for the final case, the load was applied, and I'm talking about the condition that I'm calculating the stresses that pore water pressure after a very long time. So I would say at that time all that excess pore water pressure has been dissipated by the loss of water. So by the loss of water, we can write here, also, there's dissipation of excess pore water uh, by releasing the water, by loss of water from the drainage phase, by the loss of water from the drainage phase, so this is the statement here we have for the final case. After the long time, your excess pore water pressure becomes zero. That is the dissipation of excess pore water pressure by the loss of water from the drainage phase. Okay, and I would say now that means that extra stresses would be taken by the solids now. Extra stresses is taken by solids now. Soil solids. Can we say that? And that extra stress is actually equals to Q. That's actually equals to that small Q, surcharge, at final stage. So that was all about what you call as pore water pressure and effect of that external load on that pore water pressure. Now let's go for what you call as, yeah, we need to write here for this dissipation of excess pore water pressure. Now finally, this condition, because we are draining the soil, we're allowing to lose the water from the soil, and this condition we call it as soil is in drained condition. Soil is in drained condition. So soil is in drained condition means your excess pore water pressure has been dissipated. Excess pore water pressure has been dissipated. That means excess pore water pressure in the pore water is actually zero. If that has all dissipated, that means excess pore water pressure in the soil, that so those pore water is actually equals to zero. And at that time we say that you are because of surcharge, the pressure induced, because of surcharge, induced in pore water is equals to zero. Pressure induced in pore water is actually equals to zero. So that's the statement we have. Because of the external loads, because of that external load surcharge, your pressure induced in pore water is actually zero. That's also corresponding to this condition. That means the soil is in drained condition. And if there's no drainage, if there is no drainage allowed, that means the soil would be in undrained condition. If the soil is in undrained condition, undrained condition. What that means? What is that? What does that mean? What that means here? Let's say that you have the soil, you have the soil, you have this what you call as water table, you have the surcharge Q. Now you are not allowing the drainage to happen. So drainage is not allowed. So this valve we are going to close. Valve is closed. So drainage is not allowed. Drainage not allowed. Okay, drainage is not allowed. So So for that case, I would say that it is similar to that of case B. It is similar to that of case B. That means your excess pore water pressure is still there. Your excess pore water is still there, and that is equals to Q. So this is actually corresponds to condition of case B. Corresponds to case B. That means your it's talking about the immediate condition. It's talking about the immediate condition. Immediate condition. It's similar to that of if I'm not allowing for a long time, if I'm not allowing for a long time that if I am not allowing that drainage to happen for a very very long time, that means going to keep for I'm going to keep the value closed for uh, large number of time for a long time. That means it's similar to that of that case, that is immediate case. It's similar to that of immediate case. That means for all time your pore water pressure is excess pore water pressure would be equals to surcharge Q for all time I would write for all time. If the soil is in undrained condition, if I'm not allowing that what you call as drainage that if I'm not allowing drainage, if it's not allowed, okay, that means all that extra load the of Q into A is taken by the pore water. So that was all about what you call as pore water pressure. Let's go for the third kind of stress. Let's go for the third kind of stress that we call it as that's our important one. So that's we call it as effective stress. So third one is there. That's called as effective stress. And the name of this topic is actually based on this effective stress. So effective stress we denote it by as sigma bar, and we say that this one is actually not. This is not a physical parameter. This is not physical parameter. But the other two sigma and u, they are physical parameters. That means they are measurable, and this one is not measurable. Still this is very very important. Physical parameter. It's not physical parameter. I would write it is not a physical parameter. It's not a physical parameter. Let's go for what is this actually. Is this effective stress all about? Let's analyze the soil mass. Let's take a soil mass. Let's take a soil mass, and I would say there are at let's zoom let's zoom in. I would say there are few soil particles, and they are in the contact. 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 Let's have the contact. Let's have the contact. Let's have the contact. Let's say these are your few particles, few soil particles. They are in contact with each other, and I would draw the cross section x such that it crosses the contact of those grains, contact points of those grains, contact points of those grains, soil solids. Let's say that this is our cross section. This is your cross section x, and it's touching those what you call as it's trying to touch those grains, contact points. Okay, so this is your cross section, and we call this section as that this is a wavy section, or this is some curved section. It depends on that those particles orientation, and we are going to talk about the contact force. What is the contact force there, and what is the contact stress? So it's some sort of this effective stress is somewhat talking about the contact forces, of that soil solids. So let's say that there's some contact force here between the particles. Let's say that there's some contact force. There's some there's some contact force. There's some contact force. Okay, there's some contact force, and I want to take that. Let's say that the weight above that cross section. Let's say that this is the weight above that cross section. Weight above the cross section. This is the total weight above the cross section. Let's say that this is there's some surcharge also. There's some surcharge of Q also. There's some surcharge of Q also. There's the weight of the soil above. Weight of the soil above also. Let's say that weight above the that cross section of the soil is actually, let's say that this is weight of W, such that the total such that your Q plus such that your Q plus we can write there is some P total force of P, that's actually Q into area cross section plus your weight of W. So that's total force above. We can write this is total force of P above that cross section XX. So that is the total force above that cross section. Now I want to say we are going to assume this cross section. Your this cross section we can assume it it's a straight line. It's a straight line because as the solids are very small, but this is your to understand the concept where we are zooming in the particles. Actually, where our solids are very small. Our solids in the clay, they are very small. So actually, you can't see those soil particles. You can say that your cross section is actually a straight line. Your what you call as your cross section is actually a straight line. We can assume that your cross section XX plane is actually a horizontal plane. We can assume it to be a horizontal plane because solids are very small. So we can say this curvature can be ignored. This curvature is ignored. We can ignore the curvature. Okay. So this is for the understanding where we are going to zoom those particles and showing the curvature of that section. But finally, I would say I'm going to take now a cross section size that is a straight line, that is horizontal section, with the area of the cross section as some value of a. Okay. Now I would say there is some resultant force in the vertical direction because there's some contact and there would be some horizontal and vertical resultant that those uh, forces along the vertical and horizontal direction because of that contact force. Let's say there is some contact force of C1, there's some contact force of C2, there's some contact force of C3, and this is C4. So these C's are your contact forces between those grains, contact forces. Now I want to resolve those. So I would say your force in the vertical direction is some n1. So your force what you call as your component of that contact force is some horizontal component, that vertical component along the, yeah, n1 is their vertical component of that contact force. Okay, n1. Similarly here we can write there is n2. We have n2. There is n2. Similarly, so on and so on. So we're going to take those vertical components. Let's take the vertical components now. So we are going to idealize it. This is our cross section now, because we have assumed that your soil solids are very small and curvature is going to be ignored, and we are going to take this cross section as XX cross section. And let's say that the solids are placed somewhat in this fashion. Let's say these are your solids now. These are your solids, and here we have some contact force of N1, normal force N2, N3, N4, N5, so on and so on. So I would say that let's write these are your summation of all those normal components of contact forces. So this is your summation of normal components of what you call as contact forces. Okay, contact forces. Okay, and there will be some pore water also, and there is some pore water also. Pore water is also there, so that means that pore water is developing some pressure. And I would say that's some pore water pressure of U. Let's say that there's some pore water pressure also. That's also resisting that load upwards. That's downward load, total weight above. Okay, so let's say that there is some pore water pressure. This is the pore water pressure in the pore, in the pores. What do you call as in the pores? Okay, and there is some area of the pores. On which this pore water pressure acts. Area of the pores. There's some area of the pores also. So I would say by the force equilibrium, I can write the equation that summation of Fy goes to zero. If I say that your weight of total weight above that cross section, because of surcharge and because of that external total weight above, so that finally we can write this is total P of P above that cross section. So we can say that there's some P above that cross section. P above that cross section XX, and there's some those contact points where your normal forces are acting, normal N1, N2, so on and so on. And there's some what you call as pore water pressure also acting in upward direction. Pore water pressure is acting on those pores. So we can write the final equation that we have this what you call as we have this equation that we can write. Let's try to go for the equation. I would write your total force above is equals to that summation of all those contact normal component of those contact forces, summation of all those Ni plus that pore water pressure acting for the area of the pores, acting for the area of the pores. Now, if we try to divide by the area of that cross section, if we talk about the particular cross section, we are going to take a particular area of that cross section. If we talk about that cross section XX in that three-dimensional, I would say this is your cross section XX, and want to take that cross section of A. Okay, let's try to divide now. Let's try to divide this equation now. I would write P above by area cross section is equals to summation of Ni divided by area cross section plus U or pore water pressure into area of the pores divided by the area of the cross section. So we already have talked about what is the P above by A. What is this? We already talked about this. That's actually total stress. What is the total weight above the cross section divided by area of the cross section? That is the total stress. And what about this? Let's keep it as it's. And we say that you have this cross section, you have this cross section, you have this cross section XX, and at this point, your contact actually is, let's say this is your contact between the soil particles. This is the contact between the soil particles. This is the contact between the soil particles. We say that the contact area between the what you call as contact area between the soil solids, that's very less. It's less. It's less. That's we have seen that that's almost 3%. 3% of total area cross section, area of the contact. We say that total area of the contact is actually only 3%. That means 97% is the area of the pores. So area of the pores is actually 97%. 97% if we take that cross section now. So 97% is almost equals to 100%. So this is almost equals to total area of the cross section. So finally we have this assumption here. So we can ignore now. We can say that area of the pores is almost equals to total area of the cross section. So such that your U by A, yeah, A by A gets cancelled, and you're only left with what you call as small u, small u. That's pore water pressure. That's actually pore water pressure. So we say that this is pore water pressure is acting for the area of the pores, but we assume that that we can ignore the area of the that contact forces, area of the contact between soil grains, such that your area of the pores is almost equals to total area of the cross section. Okay. Now, now, what about the summation of Ni divided by A? What this means? What this means? Can you tell me what this means? So we can write this for this one. We can write what this means. So we can write that what is the summation of Ni divided by A? So this is actually summation of sum of normal components, sum of normal components of contact forces between soil grains, solid grains, solid grains, and divided by the total area of the cross section. Area total of yeah, we can write gross area of the cross section. Total area of the cross section. Can we write that? So this we call it as effective stress. This we are going to call it as effective stress. So this is your effective stress definition for your effective stress actually. That's your sum of the normal components of that contact forces between the soil solid grains divided by the gross area of the cross section. So this one is actually, we say this is non-measurable. We can't measure it. So this is not a physical parameter. That's why this is not a physical parameter, because you can't say what is the contact. You can't tell me what is the contact, or how much force is there in a normal component of those forces. What is the contact force, and what is the normal component of that? If you have soil mass is there, and you have infinite number of those soil particles, and you would tell me what is the contact forces on what is the contact forces, and finally what is the normal component of those forces. That is difficult task to perform. So that's why it's not measurable. It's not measurable quantity, so it's not a physical parameter. So this is actually derived now. This is actually derived from we can calculate this total effective stress from difference of total stress minus, we can write total stress minus pore water pressure. So this is your final equation. That is, the total stress is actually effective stress plus pore water pressure, and that means your total that effective stress can be calculated by that summation. That is the sigma minus u, total stress minus pore water pressure. So that's one more definition we can write, that your total that effective stress is actually Effective stress is actually total stress minus pore water pressure. Total stress minus pore water pressure. Now, we see that this is not a physical parameter, this is not measurable, but this is very, very important. This is still very, very important. Still, this is very, very important. Very, very important. This is very important as compared to total stress as compared to pore water pressure. Because all the properties of your soil, they are related to what you call as, they are directly related to, they are directly related to total effective stress, directly related to effective stress. All the properties I'm saying, all properties I can write. The properties I'm going to write here, let's forget all. I'm going to write the properties. So the properties here, that are the chapters in themselves. We can say one of the chapters, that's compressibility, compressibility, compressibility property of that soil, consolidation, settlements, settlements are there, settlements are there, shear strength of the soil is there, shear strength of the soil is there, or shear stresses that gets developed, shear stresses that gets developed, and load bearing capacity of the soil. So these are your chapters of your geotech, and I would say all those properties of your soil are related to effective stress directly, and they are not directly related to total stress. They are not, these properties are not directly related to total stress, but they are related directly to the what you call as effective stress. So effective stress is very, very important tool for your geotechnical engineering. So even though we can't measure it directly, but we can measure it by the difference of these two, and this one is measurable, this one is also measurable, and finally we can also get this value by the difference of the two. So that's all about what you call as the total stresses that are the total stress, pore water pressure, and effective stress in your soil mass. I would say thank you for watching our lecture. Now we can have final touch. We can have final touch for your that effective stress calculations. Let's say this is your there's some external surcharge Q. We are having that soil dry, and there's some water table. This is height of H1, this is height of H2, and we want to talk about that section somewhere here. Let's say that this height is H2 after that section, XX section, and we had that point O. Now I want to say what is the effective stress at that point O. So actually that would be calculated if I know what is the stress at that total stress at that point O, and what is the pore water pressure at that point O. At that point O. So I would say your total stress is actually how much? So that's actually total Q. And we want to talk about long time, that after a long time, after the long time surcharge has placed, after a long time surcharge has been placed. So I would say that that's actually equals to total stress is actually the total weight above the cross section. Total stress is actually total weight above the cross section. That's actually Q plus gamma dry. This is your dry soil, so gamma dry into head H1 plus gamma sat into height of H2. This is your saturated soil. So similarly, your pore water pressure is only because of the water. I would say here you insert the piezometer, you would get the level of water up to this point. That's up to the water level, water table. So that's your height H2. So your pore water pressure is gamma W into height H2. So that means your effective stress is equals to sigma minus U. That's Q plus gamma D H1 plus gamma sat H2 minus gamma W H2. And we know that we have that gamma submerged. What was the equation for gamma submerged? Okay, this is your equation. So we can say that your H2 is there, H2 is there. So we can write finally your effective stress at that point is actually that total surcharge into dry plus gamma dry into height of H1 plus gamma submerged for the height of H2. This is your effective stress at that section OO, section XX. Okay, so that's all about what you call as total stress, pore water pressure, and effective stress. Thank you for watching our lecture. Okay, thank you.